So let's take a look at the ideas behind assignment 7.1 on freshwater resources. Let's start with hydrology. Just a little review here. Don't have to say much because we studied this in our last unit, but you do see infiltration happening here, and that's bringing water into the groundwater. And the rate at which the water goes through is called percolation, or the process is called percolation. The rate is called perk rate. And we got runoff here. And let's just point out here that we got evaporation not only from water but even from soils. And let's not forget that transpiration from trees is actually a very big component of how water gets returned back into the atmosphere. So of all the water available on the planet, 97.5% of it is salt water, leaving only 2.5% as fresh water. And of that, about 80% of it is frozen in the ice caps at the poles or in glaciers. 20% of it is in the ground, and only 1% of it is on the surface. So we have very little access to fresh water without having to use wells. And the fresh water on the surface, most of it is in lakes, and the other part of it is just soil moisture. And then you can see the rest of this here is water within rivers and atmospheric water vapor. And so here's a watershed, which is just defined as a land area that drains into a particular waterway. And we see some dotted lines here. All we're trying to show here is that whatever water lands on this land is going to go into this creek. So this is a watershed, and whatever water lands on this land over here is going to drain into this other creek. So that's a different watershed. But you can look at it on a bigger scale and see that the entire land around here is going to drain into this central creek or river. So it's one large watershed. And San Marcos is in the Atascadero Creek watershed. So we can see here, whatever water runs off in a big storm when we get lots of inches of rain per hour, if there is trash on our campus, it's going to find its way into this creek here, which goes through this neighborhood to the Atascadero Creek, and then from there on to Goleta Slough, where it empties into the ocean. So let's do a review of groundwater here. We say that groundwater is stored within aquifers, and aquifers are rocky places where there's space between the rocks that can hold water. And what keeps the water from going down deeper would be a lower laying of clay. And if you happen to have a layer of clay above your aquifer, then you can get what's called a confined aquifer. And that means the water can become pressurized. And in that case, if you were to dig a well, the water could come up from its own pressure, and that's called an artesian well. But in most cases, like in my house here, we have a well which we tap into an unconfined aquifer. So we have to use an electric pump to bring the water up to the surface. And the water table is that line which is how far up the water comes in the aquifer. And sometimes when we talk about springs, that is where water comes naturally out of the ground, and that can be from a confined aquifer where the pressure of it brings the water up. And here's another diagram, and we're seeing in areas where we extract water from a well, we see a drop in the water table, and that's called a cone of depression, when the water table drops below because extraction is faster than the groundwater flow to replace it. This groundwater does flow extremely slowly, which is one reason that we're so concerned about not polluting it, because if you do pollute your groundwater, that groundwater typically can stay there for like 100 years or more, and it flows so slowly that it takes a long time for those pollutants to get flushed out. And because it's so dark and cold there, you basically get very little bacterial action. And bacteria are very good at breaking down pollutants, but because of the conditions there, the bacteria work too slowly. And let's take a look at this other diagram here. We see a recharge zone where the water that lands can infiltrate into the ground and therefore raise the level of the water table. So it's recharging the aquifer. And we see the area where the water table is dipping by the well. And here's another term that that you should be familiar with, called the Vados zone. I say that a little bit hesitantly because would be surprised if you actually saw in the AP test, but you can write it down. So Vados just means the area above the aquifer where it's dry, basically. And we also see here that the water table is increasing because of the stream right above it. So water's coming in. And here we have something called an effluent stream, and that's the opposite of this influent stream, because influent is from runoff accumulating, but the effluent stream is actually where groundwater is going, seeping out of the ground to make a stream. So it's discharging. With discharging in this case being the opposite of recharging. So it's kind of funny because here the stream is putting water into the ground, and here the ground is putting water into the stream. So this would be also called a spring-fed stream. And we actually see a case in Santa Barbara here. If you were to get off at the Castillo Street exit off of the 101, it's almost always wet right underneath where you're going under the freeway, because apparently right there the water table is high enough that it's above the surface of the pavement. And the city has spent lots of money to try to fix that problem. And here's just another diagram. Nothing much new to show here, but here's that groundwater table again. And here's some terminology or some things you can write down. So if you want to pause it, you can write down some of those ideas. I'll just mention here upper zone of aeration, lower zone of saturation. So above the water table, you have the zone of aeration, which means it's air. Below it, you have the zone of saturation, meaning it's saturated with water. Okay, so aquifers can be of these two kinds, and we've discussed it already. You can pause and write down some of these ideas. And let's go to lakes and ponds. So here's a little diagram, and you can see we have sunlight coming in here, and that creates in the zone that we call the limnetic zone. And I think of limnetic as related to lumens, which is one unit that we use for measuring the brightness of light bulbs. So it refers to light, and because there's light entering this top layer, you're going to get photosynthesis by algae and plants. So you're going to have lots of oxygen available. And the next layer down, you have the profundal zone, and this is where the light cannot penetrate because it's been absorbed by the layer above it. And so there's not a whole lot of activity going on there. But then you get to the bottom layer, which is the benthic zone. And here you also do not have photosynthesis, but you do have a lot of life happening there, especially decomposers, because whatever dies in these upper regions here is going to sink. So algae, as it dies, is going to sink and settle. Same thing with any insects or fish or whatnot. So you have a lot of microbial decomposition happening down here by bacteria. And that means there's a lot of nutrients available in this lower region here. But what you don't have is much oxygen, because the oxygen is mostly at the top where the photosynthesis is occurring. And oxygen can also come from the air and diffuse into the water as well. We'll point out here the littoral zone, and that just means the area along the edge. And there's a lot of plant life along that area, which means there's going to be high biodiversity of insects and amphibians and reptiles that might eat those insects, and birds that might eat the insects or possibly the amphibians and reptiles. So that's an important habitat for the ecosystem. So here's some basic things that you can write down. We just discussed them. Okay, moving on to cultural eutrophication. We saw this term already in our study of the nitrogen cycle. But here, cultural just refers to eutrophication that's not happening naturally. It's happening because of human activity. So it means it results from too many nitrates and phosphates, primarily from agriculture runoff. On the left here, we see a healthy water body that's low in nutrients, so it's clean, and it's called oligotrophic. And because you're not getting eutrophication, you have high oxygen. It's a natural state of how waterways should be, and it's the opposite of eutrophication. So if we go over to this image here, we see eutrophic water. It means it's polluted with lots of nutrients, and it has low oxygen as a result of all the decomposition that will happen with that organic matter. And so this is the unnatural state. Let's do a little review of wetlands here, or an introduction perhaps. Wetlands include freshwater marshes, swamps, and bogs. They are wet areas with lush vegetation, and they are especially productive and valuable for wildlife. When we see that word productive, we should think that a lot of plants and algae grow there. Yet they are often destroyed by human development, as they occur in flat areas that can be developed if drained. One of the most common things to do with wetlands when you fill them in is to build an airport or use it for agriculture, because both of those require generally flat fields. Wetlands provide very important environmental services, and that just means that they provide benefits to us as humans. And so they do that by, number one, slowing runoff, which allows water to infiltrate and recharge aquifers. One of the wetlands that we saw at UCSB, that area there, when we get big storms, you get a lot of water from the creeks running through that wetland area before it goes off to sea. And so it's important to have wetlands to be able to catch that storm runoff and let it sit for a while where it can then infiltrate. And while it's sitting there, it's also being filtered of pollutants through biological uptake. So these plants can actually help remove contaminants in the water as they bring water into their roots. And you also have bacteria that can break down pollutants as well in that water. And they also protect shoreline habitats from severe storms such as hurricanes by slowing down tidal surges and blocking wind. So here we see some mangrove trees, which you commonly find in Florida and the Everglades. And they're really important because, for one, these are pretty tall trees, so when you get big storms, they can block wind, so that when it reaches cities and areas like that, it's going to cause less destruction to our buildings. And also these tidal surges. When we get storms, you get big waves coming in. And when the waves hit these trees, their energy is going to be dissipated or reduced. And this can all, of course, help reduce erosion that normally would result from those big waves. And let's point out here a little fact. Over 50% of all original wetlands in the U.S. have been drained and or filled for agriculture or development. And right now there's a movement to try to restore many of these wetlands. And so in the Bay Area here, wetlands formerly dominated the Bay Area before being drained, which means leveed or filled. So if you're gonna drain a wetland, it means you build a big barrier around the edge, and then you kind of like put a pipe in there to help drain it out. And the barrier or levee that you put around the edge is keeping water from going back in. And so here you can see areas that still have existing marsh, not a whole lot, and all these other areas have been filled in or leveed. And so the Sacramento River here is an important water source for all the irrigation happening in the Central Valley there. And many of these surrounding wetlands have been filled in for doing that agriculture. Alright, let's conclude this part of the slide with our discussion about glaciers. They are large bodies of ice that move slowly down a slope, valley, or wide area of land. And together with ice caps, they contain most of the world's fresh water. And this here we're seeing is Bering Glacier in Alaska, the biggest one in the US. And it melts a little each year, releasing more than twice the amount of water that is in the entire Colorado River. So this actually is an important part of the water cycle for all the fresh water that it releases to our surface waterways, making that water available to us. And I think we'll stop there for this part, and the next part we'll take a look at freshwater use, or in most cases, overuse.